So welcome back, and we are entering into Unit 4, which is all about probability. So where we last left off was identifying this idea of randomness and being able to do simulations. And now we're going from randomness to probability. So as we travel on to the new year, we're starting with Chapter 14. Unit 4 involves 4 chapters. So by the end of this week, we should be able to finish these problems posted on Schoology, with the objective being to calculate the probability of random events. So just to get started, get some terminology in place. If we're talking about a random phenomenon, it's a situation in which we know what outcomes are possible, but we don't know which particular outcome will happen. So each occasion upon which we observe a random phenomenon, rolling a die, flipping a coin, is called a trial. At each trial, we note the value of the random phenomenon and call it the outcome. So whatever, we flip the coin, we do the thing, we get the outcome. When we combine all of the possible outcomes, the resulting combination is called an event. So the collection of all possible outcomes is called the sample space. All of the possibilities are listed out in front of us. Now, here's our first introduction to this key term: independent events. When thinking about what happens with combinations of outcomes, life is much simpler if the individual trials are independent. So, in a sense, independent means that the outcomes of one trial does not influence or change the outcomes of the other. So, for example, coin flips and rolls of a die are independent. You flip a coin, it's not going to affect rolling a die's outcome. We show events are independent by demonstrating the probability of a second event is not influenced by the result of the first event. So this is where we get into this tricky notation. So this is saying the probability of A is equal to the probability of A given B happened. So this is our first introduction to this idea of conditional probability. I want you to get used to this notation, probability. So yeah, the probability event A equals the probability of event A given that B occurred. Now, if you have your formula sheet in front of you, we will learn that the probability of A, this is the probability of A and B divided by the probability of B, or on your formula sheet for the AP Stats test, the probability of A, event A, times the probability of event B is equal to the probability of A and B happening. And yes, this upside down U shape means and in our set notation. So that's key idea 1. And independent events is very, very useful. The next main big idea, and again, we're going to go back to that PBS documentary just to talk about in a little more context of the law of large numbers. So the law of large numbers and what Las Vegas is built on says that the long run relative frequencies, which is empirical probabilities, of repeated independent events gets closer and closer to a single value, which is what we call the theoretical probability. So this single value is the theoretical probability of the event occurring, which many of you guys think if you roll a die, what's the chance of getting a 6? It should be 1/6. But empirical, meaning the experimental values, are different than our theoretical conditions. So this definition is based on repeatedly observing an event's outcome and is called empirical probability. The law of large numbers says nothing about results in the short term. So if you go to the casino, you want to go to downtown Detroit and want to put a bet, if you just gamble one time, you may win, you may lose. But the reason why casinos are in business, and why we're going to watch this video in just 1 second, is because the law of large numbers says in the long run, they're going to make money. They have built-in odds for them to win. So let's watch this little clip, and then we'll come right back to the notes.
Ultimately, all the predictive power of statistics rests on a revolutionary insight from about 500 years ago. That chance itself can be tamed through the mathematics of probability. Viva Las Vegas. Here's a city full of palaces built on understanding probability and fueled by gambling. Which may seem a funny place to find mathematician Keith Devlin. But mathematics and gambling have been tied together for centuries. Today in a casino, you'll find roulette, slot machines, blackjack. Playing craps is also known as rolling the bones, which is more accurate than you might think.
Humans have been gambling since the beginnings of modern civilization. The ancient Greeks, the ancient Egyptians would use the ankle bones of sheep as a form of early dice.
Surprisingly, while the Greeks laid the foundation for our mathematics, they didn't spend any effort trying to analyze games of chance.
It seems to have never occurred to them, or indeed to anybody way up until the 15th, 16th century, that you could apply mathematics to calculate the way these games would come out.
16th century Italian mathematician Girolamo Cardano made a key early observation. That the more times a game of chance is played, the better mathematical probability predicts the outcome, later proven as the law of large numbers. Examples of the law of large numbers at work surround us.
When I flip this coin, we have no way of knowing whether it's going to come up heads or tails. That time it was heads. On the other hand, if I were to toss a coin 100 times, roughly 50% of the time it would come up heads, and 50% of the time it would come up tails. We can't predict a single toss, we can predict the aggregate behavior over 100 tosses. That's the law of large numbers.
In fact, casinos are a testament to the iron hand of the law of large numbers. The games are designed to give the casinos a slight edge over the gambler. Take American roulette. On the wheel are the numbers 1 through 36, half red and half black. Betting $1 on one color or the other seems like a 50-50 proposition. But the wheel also has 2 green slots with zeros. If the ball lands in those, the casino wins all the bets on either red or black. And that's the kind of edge that makes the casino money over the long run.
Customers are gambling. The casino is absolutely not gambling, because they may lose money, they may lose a lot of money to 1 or 2 players, but if you have thousands and thousands of players, by the law of large numbers, you are guaranteed to make money.
The law of large numbers comes into play outside of gambling, too. In basketball, a field goal or shooting percentage is the number of baskets made divided by the number of shots taken. But early in the season, when it's based on a low number of attempts, that percentage can be misleading.
At the beginning of the season, a less skilled player might get off a few lucky shots in a row. And at that point, they'd have a super high shooting percentage.
Meanwhile, a very skilled player might miss a few at the beginning of the season and have a low shooting percentage. But as the season goes on and the total number of shots climbs, their shooting percentages will soon reflect their true skill level. That's the law of large numbers at work. A small sample, like just a few shots, can be deceptive, while a large sample, like a lot of shots, gives you a better picture. The gambling observations that led to the law of large numbers were a start. But what really launched probability theory and opened up a door to a whole new way of thinking about the future was a series of letters exchanged between two French mathematicians, Blaise Pascal and Pierre de Fermat, in the 1650s, about another gambling problem that had been kicking around for a few centuries. A simplified version of the problem goes like this. Two players, let's call them Blaise and Pierre, are flipping a coin. Blaise has chosen heads and Pierre tails. The game is the best of 5 flips, and each has put money into the pot. They flip the coin 3 times, and Blaise is ahead 2-1. But then the game is interrupted. What is the fair way to split the pot?
The question is, how do they divide up the pots so that it's fair to what might have happened if they'd been able to complete the game?
Fermat suggested imagining the possible future outcomes if the game had continued. There are just 2 more coin flips, creating 4 possible combinations: heads, 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 tails, tails, heads, and tails, tails. In the first 3, Blaise wins with enough heads. Pierre only wins in the last case. So Fermat suggested that a 3-1 split was the correct solution. The key breakthrough was imagining the future mathematically, something even Pascal had trouble with.
Because what Fermat did was say, let's look into the future, look at possible futures, and we'll count the way things could have happened in different possible futures. It was a simple arithmetic issue, but the idea of counting things in the future was just completely new, and Pascal couldn't wrap his mind around it.
Eventually, Pascal accepted Fermat's solution, as did others. And today, that exchange of letters is regarded as the birth of modern probability theory.
People realized the future wasn't blank. You didn't know exactly what was going to happen, but you could calculate with great precision what the likelihood of things happening were. You could make all of the predictions we make today and take for granted, you could make them using math.
Many people will want to think with theoretical versus empirical probabilities. Theoretical probability is based on the idea that each event in the sample space is equally likely. So if you flip a coin, it is theoretically likely that head and tail are equally likely. If we draw a card, each card in the 52 deck of cards is theoretically equally likely to be drawn. Empirical probability or experimental probability is based off of observation, actually doing the thing. When we flip a coin many times, we find the ratio of heads to total number of attempts. If we draw a card, we draw many, many cards and find the relative frequency of drawing each card compared to how many we drew. Those ratios are the empirical probability. And so this subjective thing, this personal thing, is determined by a guesstimate, usually with someone with experience. And so we're going to avoid subjective probability. Okay? We're just going to focus on theoretical and experimental. I do want to point this out. This is often, the law of large numbers is often confused with the law of averages. There is no law of averages here. Okay? There's no idea that in the long run everything's going to go to the average. It's not true. Relative frequencies even out only in the long run, and this long run is a really, really, really long. In fact, it's like infinitely long. For any of those in calculus, this is what we're talking about, the limit as our values go off to infinity. If you haven't taken a calculus class, that's totally fine. You don't need to know that notation at all. Just know that when we're talking about in the long run, it means forever. So the famous law of averages, which is also called the gambler's fallacy, is this idea that an outcome of a random event that has not occurred in many trials is due to occur. Let's say you flip a coin and you get 4 heads in a row. Well, the gambler's fallacy, or the law of averages, says, well, it's got to be a tail the next time, even though the next outcome is just as likely to be 1/2 heads. So this fallacy is probably a misinterpretation of the law of large numbers and this idea of regression towards the mean. So over many, many, many trials, the relative frequency, or the empirical probability, will tend to the expected value, which is what we call the mean when we're talking about probabilities, or the theoretical probability. Let's keep piecing this together. So the first idea is we need to learn how to count. And you're like, Mr. Swenson, I know how to count 1, 2, 3, 4, 5. It's different when it comes to different sample spaces. And so I want to go back to this idea of visualizing. If the sample space is relatively small, it's worthwhile to just write out all of the different ways you can have this happen. So either in a list or in a tree, if you want. And we call this a tree diagram. As you recall, what's the first 3 things you should always do in statistics is draw a picture, and draw a picture. So let's say if you flip a coin 3 times, what would the sample space be? Which means what are all of the outcomes that you could have? You could have 3 different flips. Each time you could have a tail or a head, a tail or a head, a tail or a head. So that's 2, 2, and 2, which means there's a total of 8. Well, let's just say you could have head, 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 or head, head, tail, or head, tail, head, or tails, heads, heads, or heads, tails, 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 heads, tails, or tails, tails, heads, or tails, tails, tails. 1, 2, 3, 4, 5, 6, 7, 8. Another way, this tree diagram would say, okay, in this bifurcation, what's happening? In our first flip, we could have a head or a tail. Then, in each of those successive flips, what is the outcome of the next to occur? We could get a head or a tail there. If we got a head, then we would have another head or a tail. Or this tail, we could get another head or a tail. Or heads, tails, heads, tails. At the bottom, 1, 2, 3, 4, 5, 6, 7, 8 gives us our sample space, how many different outcomes we got. Our total would be how many ways we got each. Once we have our sample space, we can ask slightly more interesting questions. So to separate out sample space versus the event that's occurring, because this is clear with vocabulary, what are we talking about in terms of the event and how many different ways we could have that. So if we're talking about flipping a coin, the sample space is either head or tail. If we're rolling a die, we're talking about how many different ways we can get one of the 6 numbers. So we get 1, 2, 3, 4, 5, or 6. If the event is a true-false question, the sample space is either true or false. If we roll 2 die, then we have 1, 1, 1, 2, through 6, then we do it again. If you flip 2 coins, then you have more outcomes. Heads, 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 tails, tails, heads, tails, tails. We get the idea that the event lets us focus on how many different ways we can have these outcomes. And when they're small, it's easy to count. So with simple probability, the probability of an event is the number of outcomes in the event divided by the total number of possible outcomes, or all of the number of ways in the sample space. Note the notation. I'll be expecting you to write the probability statement in the form of P of E for every probability you compute for the balance of the year. So the probability of the event that occurs. You will be writing lots of probability statements. And so when you have this, we're going to say probability of getting a head, or we're going to say probability of getting a 1. We're going to write out what we are looking for, so we list out what we are finding. With theoretical probability, it says the probability of the event occurring, or P of E, is the number of outcomes in the event E, or N of E, divided by the number of outcomes in the sample space. This is the formula you're going to see on the AP test. The number in the event divided by the number in the sample space. Again, with theoretical probability, a classic probability assumes that all outcomes in the sample space are equally likely to occur. That is, equally likely events are events that have the same probability of occurring. For example, for a card drawn from an ordinary deck, finding the probability of getting a queen, it's 4 queens out of 52 cards, or 1 in 13. If I ask you what's the probability of getting a 6 of clubs, no, I want to find the probability of 6 of clubs. No, that's 1 out of 52 cards. If I ask you what's the probability of getting a 3 or a diamond, we would say, oops, the probability of 3 or a diamond, well, there's 4 3s. Probability of a 3 is 4, the number of ways. The probability of getting a diamond is 13, but that says 16. Well, that's because the probability of a 3 plus the probability of getting a diamond, that's 17, but I double counted the probability of getting a 3 and a diamond. And so this is the formula for an OR statement, or B. I wrote it here. I'll make U is OR in set notation. So instead of using 2 letters, we use 1 symbol because mathematicians are lazy. Let's say we were looking at the probability of rolling an even sum on a pair of die. So 2 ways we could think about this. First, we need to figure out how many different ways can you roll a die. What I like to do is draw spaces for each event. There are 6 numbers on a die. There are 6 numbers on a die. I have 2 events going on at the same time, so I multiply those. That gives me 36 different events. Now, I want to know how many ways we can get an even sum on a pair of dice. So what I've done for us is written out all of the ways you can get the numbers in the sample space for rolling 2 die. And then I want to add up everything that gives me an even number. 1, 1, 1, 3, 1, 5, 2, 2, 2, 4, 2, 6, 3, 1, 3, 3, 3, 5, 4, 2, 4, 4, 4, 6, 5, 1, 5, 3, 5, 5, 6, 2, 6, 4, 6, 6. Or half in each one of those, which gives me 18. So we say, what is the probability of getting an even? That's our event. We have 18 out of 36, which simplifies to 1/2, or a 50% chance of getting an even sum. Well, what if it says, what's the probability of rolling a total of 4 on the 2 die? So again, our sample space doesn't change. It's 36. But how many ways can you get a way of rolling a 4? Well, it would either be a 2-2, or a 1-3, or a 3-1. In this case, order matters. First die, and then the second die. There's 3 out of 36, or 1 out of 12 ways of rolling a sum of 4. Last example, just for this video, keep it short and sweet for you guys. If a family has 3 children, find the probability that exactly 2 of the 3 children are girls. So in this case, we have 3 spots. We have 2 options, a boy or a girl, that can be in each. So there's a total of 8 items in our sample space. 2 boy or girl, boy or girl, boy or girl. I would just suggest you write out all of the different ways you can get this. So we have girl, 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 3 girls. 2 girls and a boy. A girl, boy, girl, or boy, girl, girl. Girl, boy, 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 girl, boy, 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 girl, boy, boy, boy. I want to know how many ways we can get 2 girls, 1 boy. I have 3 out of 8. And notice this is the probability of getting exactly 2 girls. Another way you could write this is we have our first child could be a boy or a girl. Our second child could be a boy or a girl. Boy, girl. And then our third child could be a boy or a girl. Boy or a girl. Boy, girl. Boy, girl. If we're using this tree notation, we would have, I want to walk down the tree to figure out how many ways I can get 2 girls. So this first one, we can't. 1 gives me 2 girls, 1 boy. Girl, boy, girl, or girl, girl, boy. I have 3 paths that give me exactly 2 girls, which again is what we found above. Our second portion of the video, we're going to talk about empirical probability and how it could differ from our theoretical probability. So I will see you in the next video, Falcons.